So Unikraft, that's a new project which is covered under, well, let's say it's an incubator open source project, part of the Zen project, and also covered by the Linux Foundation. And it's all about Unikernels in this project. So let's see if I get you guys convinced, because my aim is to get as many contributors to this project and get this thing growing, because it's a super nice topic actually for me. So, what are Unikernels? So what are they for, and what are they actually? I don't know if anybody if you heard about that already. So, but I'm pretty sure that you heard about this container craze, right? Everybody is running their services in a container. You hear a sentence like Google runs all its services in a container. Then you have suddenly things like Amazon Lambda, Google Container Engine, and Azure Container Services, and so forth popping up. But why are containers so popular currently? The thing is that if you deploy your service with a container, you get some benefits. For instance, very fast instantiation times of your service, like in the order of hundreds of milliseconds. You have a really small memory footprint for each of your container, for instance, a Docker container and so forth, which basically depends more on the application that you have in that box. It enables you a higher density, like you can run hundreds of thousands of container instances on a single host. And if you take this and look at VMs look just, heavyweight, fat, inflexible, right? Thousand instances of VMs on a single host. I don't believe that. But at the same time, when we talk about container, we need to also be careful about some certain security risks. I'm not saying that they're there, but it's a bit more risky in terms of development. The reason is actually coming from that all the containers, they share a same kernel and also its API. And the kernel API are system calls. And this isolation is implemented by putting in checks and so forth into each of the system calls. And if you see on I/O control or get other system calls, it can get quite complex for each of the system calls. And also, if we check the latest Linux releases, the system call number is incredibly increasing compared to hypercall numbers on a hypervisor. So, of course, I don't need to tell you if one container uses a system call which is not really protected securely, and you break out, your whole system is in danger. So usually the trade-off that you have today is kind of a picking of poison choice, right? So either you go for containers, you know that they're lightweight and you have these super fast popping up services, but kind of maybe not well nice because the isolation might be a bit iffy. When you go to hypervisors, of course they promise you strong isolation because they use CPU features for doing that, but they're pretty heavyweight. But now, I hope I can break the myth with you that VMs are actually heavyweight, because we have this thing like Unikernels now. So what is it, a Unikernel? So on the left side you see a traditional VM, right? So you run your service within your virtual machine. It has a general purpose operating system underneath and some kernel features. So what is different when we run our service in a Unikernel? So first of all, we run it also in the same virtual machine isolation and protection boundary, but instead of using the general purpose kernel underneath, we built a purpose-built thin kernel layer under the application that has only the features that the application requires. And then you can do even assumptions like, since you run anyway one application in one virtual machine domain, you could even weak up the isolation between kernel and user space and can start even optimizing the interface between application and the kernel. because that kernel layer is anyway purpose-built for that application. So benefits you get even further from this specialization step where you say, okay, I have now optimized functions to enter my kernel or my driver. So in numbers, in this graph you see on the horizontal axis number of concurrent instances deployed in the system, and on the vertical axis the deployment time. And I start here with comparing the numbers, how long it takes to bring up a process. And we are roughly there in a ballpark that doesn't take longer than 10 milliseconds to pop up processes. If you use then Docker and put that process, sorry I forgot to say that process is doing nothing, it's like just a black box, here's baseline measurement here. So if you put that in a Docker, that boot time increases and we end up roughly in the ballpark of 150 milliseconds to 550 milliseconds, which is pretty good because at least it promises you to give you more protection than just running the processes blind on your system. If you compare that with Debian boots, so meaning as a representative of a traditional VM, that number goes up from 2 to 6 seconds in the best case, and when you have 1,000 concurrently running on that system, going even up to 82 seconds. So here I agree. If I see that graph, yeah, traditional VMs are really heavyweight for these agile services. But if you take now a Unikernel, so this one is called MiniOS. This is part of the Zen project. It was more for educational purposes. But if you just take that, build it, and also do a no-op in there, we are roughly already in the same ballpark than containers, meaning it shows that Unikernels are similar as fast as containers. So now you maybe heard of a recent publication that we did that we called LiveVM. So we're actually tackling into that system on the Zen system to figure out actually where it's all my time spent when I pop so many VMs. And we figured that most time is lost in the VM management code. So we replaced that, put a complete own management toolset on top, and ended up creating VMs, even if you go now up to 8,000 concurrent instances between 5.2 and 8.6 milliseconds. And it's the same Unikernel as before. And as a comparison, Docker, we run out on the same machine, which has actually 128 gigabytes of DDR3 memory. We run out at 3,000 Docker instances. So this shows that there's immense potential in Unikernels, which is not used yet. So the gains of Unikernels when you run them in a virtualized environment are fast instantiation, so we know that from Docker, but we found even it can go even to tens of milliseconds down. We have also a low memory footprint. We can achieve really high density, as you just saw on the graph. And now the more pluses come, which is due to the specialization that we can do to, let's say, optimize our kernel layers towards the application, we can achieve even higher performance. And we had some Unikernels built in the past. One was a static HTTP server that was able to cope almost with 40 gigabits of throughput. And having said that, it had only a single guest CPU assigned for this. And also the attack surface is reduced because you have less components in a Unikernel, right? And your Unikernel has also the kernel layers with it, so you don't have kind of this shared kernel approach. And the other extra is the strong isolation that your virtual machine box gives you. So now you may ask me, cool, where would I like to use it? And the thing is, depending on these technology advantages, the use cases are quite wide-ranging. Kind of you pick pick on one of the differentiators that you gain with Unikernels. So to give you some examples, fast boot times and migration times, you would like to have it for reactive VNFs, so meaning you have a DDoS attack in your telecom operator network and you pop up on the fly a blocking firewall in front of that access, and your DDoS is gone. Lambda functions as well, you boot them up for running a single function and then kill them afterwards, so you don't want to have something really heavyweight that takes forever to come up. The other differentiator is the resource efficiency, which comes from this minimal software stack. There you can imagine also for telcos, so you notice I'm having kind of a bit telco background. You could imagine you could run for each customer that you serve your internet connection a DNF, because you can run thousands of them on a single host. But also resource efficiency gets quite important when you go into embedded areas like IoT or mobile edge computing, where you don't have that many resources that you actually can waste. High performance, of course, is a super hot topic for network function virtualization, but also mobile edge computing, including other stuffs too. And then mission critical. So, as Lars said, this is quite difficult to get your code certified. Of course, we don't have this development model yet in Unikraft, but at least we can promise that the code base is small, which makes already all this, the price for verification much cheaper. Then we have the strong isolation between our systems because of the hypervisor, and this is really interesting for, you saw it, for automotive applications or any other industrial-grade virtualization solutions. So now you say, probably cool. But why don't I have a unikernel, right? Why is this not there? And the thing is, the devil is in the detail. Such optimizations that you saw of these optimized unikernels are for now manual builds. And it takes usually months or even longer to get it really working that way. And the biggest issue is actually that it's kind of a throwaway. You go through a process a couple of times again for each of the different applications because you want to specialize your kernel layers differently depending on the application that you want to port in the Unikernel. So in practice, this looks like when you take, for instance, Nginx, and you want to have a Unikernel, you would probably start to run it on a general purpose OS and see what's there. And you will notice that many libraries, many kernel features even are completely unused and not necessary to run your service. So what you then would start is like building a system, just picking these necessary pieces, which is already lots of work, especially when I say you take some pieces of the kernel out to get your Unikernel. But then, on the second iteration, you probably will start replacing, let's say, some libraries with different implementation because you figured out that application performs much better with that, or maybe you have a more resource constrained KPI. So you start tweaking and tuning the whole system until you reach what you want to have, right? And this Unikraft project is actually all about these steps. How can we simplify that? How can we reduce the amount of work that you have to do in order to get your Nginx in the Unikernel box? So when we started with this project, we had the following motivation behind. First of all, this Unikernel build framework should support everyone's use case. This means that some people are really concerned about what does your network drivers do, in sense, what does your CPU, they're really picky in which way network packets are scheduled to CPUs to process it for NFV, and others take care more about memory allocators to get better performance for different services. So the framework should support all of that. It should, for sure, simplify the building and optimization, as I promised. And we want to build this Unikernel framework also to get rid of this throwaway attitude. Meaning that hopefully, since you heard this now, more Unikernel projects are starting to build their Unikernels based on Unikraft, so that all the efforts they did to get their application run is collected in a single base and may be beneficial also for other people. And the design approach that we have chosen is everything is a library. And when I say everything is a library, I mean even decomposed OS functionality like schedulers, memory allocators, and drivers. They are all libraries. And Unikraft, for now, consists of two components. You have a library pool, which I hope we can together increase it, and a build tool that simplifies your building and optimizing your Unikernel. So we're going to talk now about operating system decomposition. What's the issue here? The thing is that, let's take Linux or BSD. These systems are usually monolithic and really tied together. What we actually want is like a library for each of these components, like a library just for supporting file systems, because you could imagine you have Unikernels that don't need file systems at all. Or you want to have schedulers as a separate library, or memory allocators and so forth. So the challenge is here to take some OSs and pick some pieces out and redevelop it in a way so that it gets a more self-contained box that you can plug in and out for your Unikernel build. So let's have a look to the library pool that I said as one component of Unikraft. So we distinguish currently between three types of libraries. First is the main library pool, which includes OS functionalities, file systems, schedulers, network stacks. And the goal is even to provide you alternative implementations. Like you have on Linux with tons of different file system implementations, and you pick the one that fits most for your use case. We want to have this for schedulers, for network stacks. Let's say you have lightweight IP, or you have the BSD network stack ported, and depending on the application, one or the other is a better fit for you. Then we have the platform libraries. These are actually the libraries that implement the thinnest layer down to your hypervisor. We have support for now for Zen. We can run on KVM. And there's one target for Linux user space for debugging purposes. And then there are some architecture lips that some CPU architectures may require. For instance, on ARM 32-bit, we had to provide 46-bit arithmetic operations in software for modulo and division. So in the ideal case now, you select your app. Then you select and configure the libs with the build tool, which I show in the next slide. And then the rest should happen magically, and you get all your Unikernel images that are optimized for these various platforms. So for instance, we would have one Unikernel image for KVM. You would have a different image for Zen, because Zen needs different drivers. The interface is different, but you can, you specialize it for Zen. And the other for KVM, and so forth. So the build tool is for now kconfig based, so you know it from the Linux kernel when you played around with that, and has some makefile magic. Actually, I learned a lot about makefile by doing this. So you have the same principle as when you build a Linux kernel. You have a make menu config, then you select your options and libraries you want to have for your application. You select your target platforms where you want to have an image built for it, and you save your config and type make, and then that's it. So to make this a bit more clear, also with a bit more a closer example, let's say we would build a Python Unikernel. We would say we take the Python interpreter and take that as an application. We feed that to the Unikraft system, and then we select like a network stack to get socket operations. Would select a fitting memory allocator, console driver, and so forth. And Unikraft builds us the Unikernel. With another example, maybe some of you heard already about ClickOS. It is a small VNF Unikernel where you actually use the Click router software, and you do the same thing, right? You select the components you need, and Unikraft builds it for you. So, any question? No. Okay. So the Unikraft open source release, we started with version number 0.2 with the codename Titan. So let me briefly introduce what we have now. The library pool consists, for now, really of basic functionality to get everything, running and up, and for people getting their hands dirty as quick as possible. So it's not full-fledged now. So I expect much more libraries in the future. But for instance, we have a memory allocator ported from MinUS, which uses the binary body allocator principle. We have libraries for debugging. We have a scheduler interface. There's soon, besides the cooperative scheduler, there's a library coming up for preemptive scheduling. Platforms we support is Zen, KVM, and Linux for now, and most of them run on both on x86 and also smaller ARM boards with ARM v7 CPUs. So when you build now with Unikraft something, let's say a library, you will bind it to this core Unikraft repository, which has internal libraries, the makefile system, and the kconfig system. So in each library, what you need to do, besides having the source code, you need to provide a config.uk, which is actually kconfig syntax to provide your configuration interface, and a makefile.uk, which gets sucked in by the makefile system to do this build for the library. You can do at the same time provide the library also externally by using an external repo. The structure is exactly the same as internal libraries, and the system, it allows you that an external library can replace an internal library, because it's just a menu item where you then select a different one. And your application in this build system is also just a library. So the same thing, you have a makefile.uk and a config.uk. The only difference is you have an entry makefile here, which looks like when you develop a Linux kernel module off tree, looks like the same thing. It just calls the makefile system of Unikraft, handing over all the paths of where your sources are, and then that system sucks everything in and builds you the bigger menu and automates the compilation. To give you a baseline example of what we achieved with the first build we could do with our tool, this is a Zen paravirtualized guest that actually just boots and comes down and shuts down afterwards and prints some debug messages that it will up. The VM image, or the VM kernel image actually, because we don't need disk files, there's nothing there, is just 32.7 kilobytes of size. In this pie chart, you roughly see how the space is distributed among the libraries that we had to select. Most of the things go to the platform library that implements the interface to the Zen hypervisor. And we can boot and print it, and since it's so minimalistic, we were also trying out what's the minimum amount of RAM we need to assign to get it actually up. And even we had to change the tool stack in order to get that. Because it's limited to 4 megabytes. So the Zen community thought 4 megabytes is the least amount of RAM we assign to a VM. We could boot it with 208 kilobytes of RAM only. So now I hope you're all convinced now. So please join us. So the project, as I said in the beginning, was accepted as an incubator project under the Zen community, which is, by the way, a really great open community and really supportive. And we need you now for our ambitious goals, because that library pool needs to increase in order to make that really useful for many people. So if you're interested, please have a look to our Zen pages and for the Unikraft project, or drop us an email on our mailing list, or even join our IRC channel. So the core Unikraft team should be present there all the time to answer some questions. And if you're kind of in the mood like, yeah, I would like, but I have no idea what I could do here, we have a huge list of open topics, even written down in the Zen wiki. So just get in touch with us. We can find something that might interest you as well. Okay, then let's show you a small demo of this Hello World Unikernel, so that I prove that it's real and not a lie. And then we can go for a question round. So this is now my development system. As you see on the bottom of the screen, this is like top, but this is the Zen version of top, so it lists you the virtual machine that they're running in the system. And on the bottom, you have my shell. So let's start with make menu config, because that's the first thing we want to do. To show you how the menu looks like. So you select first your architecture. You want to build your application as Unikernel core. And you can choose between x86 and ARM. Since my VM is x86, I keep that one. On platform, you select what you want to have. So here it's already enabled a Zen image. Let's say I also want to build an image that's optimized for KVM. Or we take also one that runs in Linux user space because of the wide debugging tools that we can use there. Then this is the library pool for now. Here we can select, unselect, or configure even the libraries. There are also some hard dependencies selected by the application already and also by the platform. So for instance, a minimalistic libc is required by the platform, so you can't unselect it, but if you have a full-blown libc, you can replace that no libc with whatever you have, let's say glibc, new libc, you name it. Yeah, they're all configurable, as you see here. In UK debug, you can enable certain debug options. Okay, then you save your configuration. Type make. And you see it builds all the libraries separately and then links the final image with the according libraries together. This looks like this in the build directory. So this is our KVM image, which is 40 kilobytes of size. And we have also a compressed version, which is 8 kilobytes of size. We have one for Linux user space, and we have here one for Zen. It's slightly bigger now because it adds a memory allocator as well. So this is a bit more code than on the slide that I showed you before. To prove you that it runs, I first show you that it runs on Linux user space. Here we go. And now I will create the Zen guest. So I have some scripts around the tool stack to simplify that a bit. Let's assign, 4 megabytes of memory. Let's start the work. And here we go. And it's already dead already. So meaning it was so quickly up and down that we didn't see it down there. So what I have added to this example is a busy loop so that I can prove that it's actually a VM. So I go to the application options, enable this, save it. So now the Unikernel is not going down anymore, it's now wasting the CPU by just busy looping. But at least you see the VM exists. And now we run it again. And now you see. So the Zen tools are not, not prepared for, VMs that come and go in seconds. So now, any questions? I put you the sources again for, that you have time to write them down. It's also possible to meet me at the Zen booth. I can show you also another demo with another Unikernel. And yeah, we can have a chat. So yeah, please your question. Yes, I know what you mean. And so that image that we have for now is built. Oh, sorry, yeah. The question was if you use KVM tool to run that Unikernel instead of Chemo for KVM. The platform library that we have for now supports only the Chemo version, and can be booted with the direct kernel boot. Let's say using a KVM tool makes definitely sense. I think it will improve the boot times for KVM as well. I know there is a project driven by the MirageOS Unikernel guys and IBM guys, which is called UKVM. So they even go one step further and provide a different abstracted hypervisor interface. But in principle, you can all integrate that into Unikraft. What Unikraft is concerned about is only that the library needs to be there to support that case. Yes. I know you could even, share the host TCP/IP stack and give sockets. Yeah. Any other question? So the question. You mean the Python library? Okay. So the question is about how to include when you build now something like a Python language interpreter as a Unikernel, how to include Python libraries into that whole Unikernel system. So for now, my answer would be either you kind of use an intermediate language of your Python interpreted. You don't run the interpreted language in a Unikernel. You would kind of compile it with Python compiler, get these object files, and build that together as an image. Alternatively, you can also use the Python interpreter, add a file system underneath, attach a disk image, and run your Python code directly interpreted and load the Python libraries from there. Yeah? Good. Yes? Mm-hmm. That's actually a good question. So microkernels is actually, so the question was how is it different from microkernels, the Unikernels? So the question, my answer is it's a different system design. Unikernels are still monolithic. So it's a single kernel image where you include the features that you need. So you don't, decompose into several server processes, your file system support and so forth into other protection domains. You keep it included in your Unikernel. So there was a question behind. So the question is, what are the ambitious goals and where do I want to go? So the target is really that this is kind of build framework for future Unikernel projects. Meaning, I would like to see UKVM, as you mentioned here in the first row, also included as a library there that simplifies you building your application as a Unikernel. Also, maybe it changes the way how you do IoT. You could imagine this is an enabler for multi-tenant IoT platforms where you run a hypervisor on a resource-constrained device, and then you deploy your IoT services as virtual machines. And since the resources are scarce, a Unikernel would be a fit if you don't want to settle on containers, for instance. So I would really want to see that project going into several directions, kind of, multiple use cases like NFV, IoT, you name it. So it should be the starting base to simplify your Unikernel project, actually. Yes? So the question is about the license that we have chosen for Unikraft. So Unikraft is a BSD 3-clause license. So I hope, that's good enough for most of the things that you want to do. So of course what you couldn't do is now taking something from Linux and put it in there, because you might get license conflicts. But you could still take the BSD network sec and put it as a library and have something feature-rich as a networking stack in there. Any other questions? So the question is about how to, select dependencies, how that works in this build tool. So all this dependency handling is now built into these config.uk files. So when you have your Nginx applications, you kind of still need to do a bit of analyzing step to understand what are the dependencies that I need. And you would write them down as library dependencies to the Unikraft system, or feature dependencies that you need. Let's say you need a socket interface, so the user would need to provide you a TCP IP stack that comes with a socket interface, as an example. Or you need a VFS, so you define, I need VFS layer, please give me one. And then you select a according library to it. So that is all bundled into these config.uk's. Another question? Yeah. Yeah. So the question is, how is this different from Erlang and Zen? I can tell you, Erlang and Zen is MiniOS and the Erlang language on top. You maybe heard also of other unikernels like Mirage OS, which is originally also MiniOS, and you have an OCaml environment, and then you even develop some drivers in OCaml. The thing is, it's not really different. It's like, you could build these unikernels with this project too. The thing is that when these projects started, there wasn't a single place where people contributed to. And this is kind of, the issue that I was mentioning, that the unikernel for now is more or less a throwaway thing. So you build your unikernel, go through all these optimization steps and so forth, but it's just for this use case, right? And it's not going back to a single place where other people could get something from it. And also the plan is also to get, let's say, Mirage running with Unikraft platform libraries underneath. Okay. Thank you very much.